So first and foremost, apologies, I'm not like a huge public speaker, so this is probably not going to be very formal. I'm just going to talk to you like your regular group of people, which you are, but you get my All right, so my name is Joshua Fowler. I'm the environmental engineer for Romac Industries. I've been with the company for about 3 years. This is kind of an offshoot of a grant program that we were working with the Department of Ecology, which got me involved with Brian and then eventually involved with Michael. And so this is kind of a waste minimization project that we've been working on that's had some offshoots with some other production benefits and stuff. And then there's my name, but then those two names next to mine, Frank and Kim Howard, those are our two maintenance guys. Between them, we probably have about 35 years of passivation experience going on there. So they're, just want to mention them because they're a very key component of this, this project. All right. So what is passivation? I guess first I'm going to start with why Romac passivates. So we passivate because we need corrosion resistance out in the field for our products to withstand the elements. And basically what happens is the oxide layer of our stainless steel components is damaged during the fabrication process from welding, grinding, cutting, those sorts of things. And what that does is it reduces the component's resistance to the corrosion. So through passivation, we can remove contaminants that affect that corrosion resistance, i.e. cause rust, that sort of thing, and leave behind other elements of the alloy. For stainless steel, that's going to be mostly chromium and nickel. And then when those are exposed to air, it restores that oxide layer on the stainless steel components and helps get that corrosion resistance back in there so those components last in the field. So what we have pictured here is the view of our passivation process before we begin the project. So this is actually a mirrored image of the room itself. So we have this exact same setup on both sides of the room. So we have two production acid tanks, and then a static rinse tank, and then a table where we also have a pressure washer hooked up for our operators to rinse off everything as it comes through the process. So what happens is a component will come in, it'll start and end up in one of these two production tanks, and then it'll passivate for about 15 minutes on average depending on the component. And then once it passivates, it'll be lifted up, brought into the static rinse tank and submerged in there for a few minutes, brought back up, and then brought to the pressure washer table where it's then sprayed off. And then once that's completed, it's out the door for the rest of the production process. A little bit more about the production tanks. So each one of the production tanks is basically a hydrofluoric bath, which we make with a combination of nitric acid, ammonium bifluoride, and water. Each one of the tanks is heated to help with the reaction process. The rinse tank is just normal like city water, and then the pressure washer is also funded or also supplied by the city water. And what would previously happen is essentially, since the two production tanks are heated, they have evaporation. And so we would refill the evaporation. What's come out from evaporation was city water, which eventually would dilute the tanks bad enough to where the batch times would be unacceptable for production levels, which would result in us having an acid spike every about 6 to 8 weeks. And what that would be comprised of is we would pump both of these tanks out and send them off as hazardous waste. We'd pump this tank out and send it out as non-hazardous waste. And then we would take a whole new set of ammonium bifluoride, nitric acid, and we would re-spike the tanks. At the time, we were using 67% concentration nitric acid, so it was a very dangerous process. We had to stop production. It was not a fun thing to do. The production guys that I mentioned earlier are in full level B hazmat suits with SCBAs. It's not something that was very desirable for us to do. It's like my house. I have multiple. All right.
We just opened the garage.
Yeah. So, and then now this is a kind of the 2.0 version that we currently have within the building. It looks very much the same, but there's some key things here that we've changed up big time. Probably first and foremost is with the help of Michael, we realized that our static rinse tank was almost probably closer to being a third acid tank than it was a static rinse tank. So what we started doing was using the static rinse water to make up the evaporation from the production tanks, which significantly reduced our hazardous waste, helped with bath variation, I'll let Michael explain a little bit more about this 6 gallons that we're taking out per the tanks in his portion of the discussion. But now that we're doing that, the recirculation, making up that evaporation, it removes the need for those large changeouts, and it's also allowed us to go from 67% nitric acid to 20%. We have a manifold where we actually do mini spikes, and at the push of a button, we're able to spike each one of the tanks. Part of the reason we went to the 20% is obviously if we plumb in 67%, we have a leak, we have a very big issue on our hands. So now we have an inherently safer process, and it's helped out with our waste minimization. And I believe, according to my notes, and I discussed this with Frank the other day, so I mentioned that we haven't been doing the large acid changeouts. We actually used to do those every 6 to 8 weeks when we would change these out. We haven't done that since September of 2021. So we're already seeing some significant changes from that. All right, and then this is kind of hard to decipher, so I'm just going to kind of explain it. But this is just some information I got from our business analytics guy, and shows some of the benefits of our change that we've already experienced. So here you can see where our consumables for the room have gone down. In 2021, we spent 39% on consumables like the nitric acid, ammonium bifluoride, some of the caustic soda we use in the treatment process on the other side of the room for our discharge permit. And then also, probably the biggest one, and the part that Ecology loves the best, is that we've had a 50,000 pound reduction in hazardous waste. Just like that. We're not having to get rid of those acid tanks anymore, so that significantly reduced the amount of hazardous waste we're getting rid of, which has us trending for 2022 to have a 50% reduction in overall cost of consumables for the room, especially waste costs, but then also a 50% reduction of hazardous waste generated for our Bothell facility overall. So we've really seen a lot of improvement in a very short amount of time. And then just to kind of segue into what Michael's going to discuss, this is the stepwise improvement strategy that we're kind of working towards in the future. And this is what Michael's going to discuss here in just a second. So that's my portion of it. Yeah, thank you.
So my name is Michael Johnson. I am the hired help for Josh and his team. I'm a chemical engineer and chemist by training, and I've been doing, I did my first Six Sigma work for IBM, the Motorola program in 1986. So I've been doing this for a while in terms of practicing this stuff, and I'm still very much a student. So as kind of learning together, there's a few things I'd like to offer you as sort of takeaways from this process. The first is to eliminate or reduce eliminating variability in a wet process or any industrial process. For example, when you're talking about your rinsing process in your PET, all of the things we're about to discuss relevant to his wastewater process is perfectly relevant to how you're using water in the PET recycling. So this is something you can take back and say, have you thought about counterflow rinsing perhaps, or conductivity control as a means of controlling your rinse process? So think about how anytime you see a wet process or an industrial process, from washing your dishes to washing your car to passivating large plumbing, what are essentially plumbing parts, right? We could cover that, but Romac makes large plumbing parts. So that is something you'll be able to take away with you. And these are kind of the stepwise things from the Romac process. Let me see which one is which here. I just opened the garage door. Right? There we go. Okay, so this is what we're talking about. When you talk about this big sawtooth pattern, that is normal in almost every industry in the world. Okay, that's almost the starting point for every place you'll walk in. As an engineer, you're walking in and you want to help somebody establish process control. You see they're using their acid bath, they're dumping their acid bath every 6 weeks. That's a business opportunity every time you encounter that. And what we want to do, and we want to encourage you to do, is reduce the size of the dumps until you can eventually get to a steady state process. So in Josh's case, they've been dumping these large, very nasty tanks every 6 weeks. And the alternative to that is taking a small quantity of the acid out once every few days. So at the current rate, they're taking only 6 gallons out per week for each one of these tanks and replacing that with fresh acid. Now the normal person will say, hey, wait, I'm throwing away perfectly good acid. Yes, you are, but you're establishing equilibrium in the process, ultimately establishing a steady state process which will eliminate variability and improve your process. And the reason it improves your process is because when you have a sawtooth process like this, when the bath is brand new, you only need 2 minutes. When the bath is old, you need 7 minutes or 10 minutes or 15 minutes, and you don't know the difference. So you always have to design your process for the worst case. So where normally they could get away with a 5-minute process, now they may have, originally they may have to do a 15-minute process, and they always have to do a 15-minute process because they don't know the composition of the bath. We don't need fancy math to do that. You can do all of this with a spreadsheet. So you can get into, you know, CSTR models and very fancy mathematics around all of this, but all of this can always be modeled in a spreadsheet. A little bit in, a little bit out. How much came out? The other thing to think about, and a concept I encourage you to think about when you're doing industrial processes, wet processes, is there are 2 kinds of processes in the universe. There's a subtractive process and an additive process. In a subtractive process, you're taking something from a part. Or you're taking, in passivation, you're taking iron from the surface so it doesn't oxidize when you place these parts in the ground, right? Or if you're washing a car, you're washing the dirt off of the car. That's a subtractive process. When you're painting a car, you're putting something on the part. And there's 2 fundamental differences, and your technical goals are different for an additive versus a subtractive process. In an additive process, your goal is 0 waste. It is achievable. It is almost always achievable to have 0 waste in an additive process. You think about it, right? If you had no overspray, you'd have no waste, right? In a subtractive process, the goal is a little different. You want to take off only the thing you're taking off and no more. So if you have a rinse process, yes, you've successfully rinsed off the hydrofluoric acid, but now you have rinse water. And we have a strategy for dealing with some of these things. So philosophically, elimination of variability, additive versus subtractive process. And those are two takeaways that I encourage you to think about, things you can use in your career, things you can take back to your manufacturing facility, or help, you know, all the way down to washing your dishes. Okay, so as Josh indicated, we started with these 2 basically big pots of water. And the pots of water, when you take a dish out of a dish bucket, the dish is wet, correct? Now the difference between the dry dish and the wet dish is what we call drag out. The mass of material taken from one bath to the next is what we call drag out. And that's mathematically a very important function for industrial processes. Semiconductors, PET, washing cars, all of those things have drag out. The difference between these baths, in this case, we've separated the 2 baths into what we call a counterflow system. In a counterflow system, we are moving our parts from dirtiest to cleaner to cleaner to cleaner, finally to the wash table, right? But the good news here is we use the same water in every case. So we put a certain amount of water here, we reuse that water here, here, and here, okay? So in this case, we've created a counterflow system using the exact same amount of water, the exact same water, in fact, that is needed in every process tank. And the advantage of that, obviously, is you're using far less water. You can mathematically model this process. We're not going to do that today. But the relationship between the number of rinse tanks and the counterflow system is the relationship between the amount of drag out and divided by the amount of rinse water. And that's referred to as the rinse ratio. Again, that's not a little out of scope, but as long as you have a little extra time, thank you. So the challenge there is making sure that you get the water used efficiently and then arranging a counterflow system. We've reduced our cycle time, by the way, from 8 minutes or 10 minutes down to 21 minutes in this case, or excuse me, 21 total cycle. What we've done on the rinse table is we used, I'm probably familiar with ion exchange or water softeners. The water softener system, we're simply taking water from the rinse table, running it through cation and anion exchange systems, and using that water as process water. This can be regenerated with hydrochloric acid and sodium hydroxide to create sodium chloride, salt water. So it's a very straightforward process once you figure out you have the tools at your disposal. In this case, again, the subtractive process, you only want to take out the dirt. You don't want to take out all the good stuff. When you throw away that 6 gallons a week of hydrofluoric acid, we want that acid back. We take out the dirt by doing what we call acid distillation. Nitric acid is volatile. So we take that out, we put the nitric acid back in the process. We have to add back The hydrofluoric. So the hydrofluoric acid, we haven't figured out how to recover that yet. Next. We need the atomic tweezer for that. But the hydrofluoric acid, the nitric acid is recovered, and that goes back into the process baths. Again, with the subtractive process, the goal is to remove, is to remove only the thing you want to take off, and in that case, is the metal oxides. Okay, now, somewhere over the rainbow, when we get this all said and done, we want to completely automate the entire process. So here we've incorporated passivation, 5 minutes per. Instead of 15 minutes in one tank, we're going to put 5 minutes in 3 tanks. The advantage of that is now you can automate the system so that each transfer is 5 minutes apart. Now, rinse systems, we don't care how long our rinse systems are. Rinse is not time dependent. But what we do care about is the amount of water used in the system. Now, again, we've got a certain amount of drag out coming in each part, divided by the number of relationships there, or excuse me, the number of counterflow systems there. And again, that number is geometric. So if you take half of the pollutant off in one and half of the pollutant off in the next, you've reduced the pollutant by 75%, right? Then an eighth, then a 16th, and it goes on forever. So just by adding process tanks and adding no more water, you can have as clean a part as you want. And you can always define your part cleanliness in advance, prior to getting to your flow designs. So if you decided, I want a part with 10 parts per million total dissolved solids, you can define that, and all you need to do is then define the amount of drag out you have, and then figure out how many rinse tanks you need to achieve that. In almost every case, and I've been doing this for a long time, almost every case, 4 rinses is about as far as you need to go. Beyond that, your water is so clean, it's almost as clean as the incoming water. So that's been my experience. 5 has been used a few times in my career. So 4 counterflow rinses. So that with the passivation system, now instead of having a single source and adding chemicals to every bath, we're going to use the same strategy, and the mathematics are a little more complicated. But using acid distillation and then counterflowing the acid back out, taking a little tiny bit of acid out all the time, and putting that acid back in the last system where it's the cleanest, maintains the baths in a system that you're also going to see the best technical results. So the cool thing about this is now we've gone from a process where we're doing 21 minutes a load, and then the operator's running around and hurting himself and bending over and doing all the things that we don't want them to do, the dirty, dumb, and dangerous, the 3 Ds. Now they can simply push a button, and every 5 minutes they get a new clean rack. So that's the end of the goal. And oh, by the way, 5 minutes and 30 seconds is a vast increase in capacity with a reduced in labor. So that's what we'll be up to that in the next 9 months or 2 years or however long it takes. But that's the goal that we're trying to accomplish. So the net result now is 50% reduction in waste and 50,000 in savings. Eventually, we'll have eliminated hazardous waste completely. We'll have recovered all of the acid. We'll have a 200% increase in capacity, and the dollar figure is astounding. And again, this grossly understates the real value of that when you start thinking about the labor costs and improved quality and quality of life for the operators. So it's a very cool outcome. That's what we have. Thanks.
Thank you very much. We still have 1 minute for a question. Little state, so we have more questions. We can have more questions later too. So any question for now? Go ahead.
Okay. So how was the process to change from hazardous waste to wastewater?
Great.
It's still the same acid going out into the wastewater.
Great.
Is there due to a regulation that the amount of acid going to the wastewater?
Yes.
Okay.
It's a rule in Washington State, actually in the United States, there's a rule called permit by rule. So it's anything where the wastewater is hard plumbed to a permitted industrial wastewater treatment facility is not designated as hazardous waste. So it's a regulatory nuance that we're taking advantage of now, and we'll be recovering that material once we have acid distillation in place. A temporary strategy.